In this video we're going to be looking at carboxylic acids. Carboxylic acids have got this general formula, so you'll see the functional group here with the C double bond to O and the C to an OH. The R group can be as small as a hydrogen for methanoic acid, or it can be any sized carbon chain. So just going to quickly go through the naming of some of them, some of the small ones, so that we can see a bit of a trend. One of the big mistakes that students make is they forget to count the carbon that actually has the functional group in it when naming it. This one here therefore has only got one carbon in it, so we're going to call this one methanoic acid. Its other name is formic acid. It's actually found in the stings of ants and things like that. This one here, 2 carbons, so ethanoic acid. And that is commonly found in vinegar. That's probably the best example of that. So you notice that these are often found in natural things. Another common carboxylic acid is citric acid, and there's also tartaric acid, both used in foods. And there's another one called salicylic acid, which is basically aspirin. So they're found in natural things. So nature makes them, but we can also make them in the laboratory. So how do we do that? Well, what we need to start with is a primary alcohol. So basically we've got an alcohol that's got this arrangement here. What we do is we oxidize that alcohol either with acidified permanganate, so what we'd observe is the purple permanganate decolorizing, or acidified dichromate, where the orange dichromate would turn a bluey-greeny colour. What that does initially is makes an intermediate thing called an aldehyde. So what it actually does is make this. So you'll see that it's lost a hydrogen from here and a hydrogen from here, and a double bond has been formed to make this. We don't learn about aldehydes this year, so I just say it in passing. Ultimately what ends up happening is you end up with that double bond staying, and now this hydrogen becoming an OH, and we get our carboxylic acid. Now, quite a lot of heat is often required, especially in the dichromate way to do this, but also heat helps drive it past the aldehyde stage all the way to the carboxylic acid. Now that causes a bit of a problem because organic compounds evaporate quite easily, so if we were to heat it in our flask, then it would all drive out the top and we'd lose what we're trying to get. We'd get some carboxylic acid, but our yield or percentage of desired product would be very, very low. So instead what we do is we do a thing called reflux. And reflux is a way to heat things without losing anything. We use a thing called a Liebig condenser, and that's this funny looking thing here. What we've got, I'm not sure if you can see on the video, but there's 2 tubes here. There's an inner tube and an outer tube. And there's these hoses that are attached to the outer tube. At this end, this is attached to the inner tube, and so is this. So if I have my reaction occurring in here, with heat being provided, then the things in here that are evaporating will go through the inner tube. Well, what I can do is I can attach the bottom hose here to a cold water tap, and that water goes around the outside tube, cooling this system down. So the gases that go into the inner tube now are very quickly being cooled down by the cold water. Just a quick note, the water has to come in at the bottom, not the top, because you need that space for the gases to recondense. Now this is all set up straight up and down, so when they condense, the gases fall back into here and continue reacting if they can react, or stay in there for purification later if they're already the desired product. So there we go, that's how we make carboxylic acids in the laboratory. We oxidize a primary alcohol using reflux apparatus. Okay, the other thing we need to know about these is something about their reactions. So what I want to do first of all is have a look at the nature of them. What I've got here is 0.1 moles per litre of ethanoic acid and the same concentration of hydrochloric acid. So we've got a strong acid and a weak acid, a carboxylic acid. I've given away the next bit. What I'm going to do first is I'm going to look at the colours that they give us with universal testing solution and compare and contrast those. And I see that there's the same amount of universal testing solution there. I can see the two different colours. This is ethanoic acid, this is hydrochloric, same concentration, so this difference in colour infers that this is a weak acid because we know this is a strong acid. How can we show that with an equation? Because we're often asked to prove things with an equation. Well, this is how we do it. The ethanoic acid is an acid, so it's got to make hydronium ions when it reacts with water. The equilibrium is showing us that it's a weak acid. It's got to make hydronium, and so that hydrogen is coming off here, CH3COO-. If this is ethanoic acid, this is called the ethanoate ion. Now that'll be important for what I'm about to show you with a couple of reactions. So if we have to show using an equation the acid-base nature of a carboxylic acid, we write this kind of reaction. Equilibrium arrow is important. Hydronium ion being formed means that it's providing hydronium ions to the solution, so therefore it is making the pH decrease below 7. Right, the next thing I'm going to do very quickly for you is compare and contrast the reactions of these two acids with magnesium ribbon. Now I'm not going to test the gases made because I'm going to assume that we remember that stuff from earlier years. Now, the one on the left is the carboxylic acid, the one on the right is the organic acid. And I'm trying to get it so that I don't get the metals in until I'm ready to. Of course it's not going to work for me this time. There we are. Okay. And we can see that there is not much of a difference. In fact, if anything, the hydrochloric acid is not behaving and it's actually reacting slower. Normally what we would expect to see here is that the strong acid would react at a higher rate than the carboxylic acid. Sadly, despite previous testing, this hasn't worked in this case. I'm just going to leave those for a second and see if that changes in a moment. Luckily I have a backup, and that is to use some washing powder or sodium carbonate the same way. We'll see if we can get a difference here. And I have chosen very low concentrations. This one does show the difference a lot better. It is actually giving a visible reaction with the hydrochloric acid. You can see some bubbles forming there slowly but surely. I hope that's in the focal length of the video. Whereas I can't see anything happening with the ethanoic acid. Now look, it will react eventually with the ethanoic acid, but at least here we can see there's some bubbles forming on this one. So why do they have different rates of reaction? Well, that's because of the dissociation. As I've shown here, this is an equilibrium, so quite a lot of these ethanoic acid molecules stay as molecules. Only a few of them dissociate to make hydronium ions. Whereas with hydrochloric acid, there is no HCl in an HCl solution. It's all hydronium ions and chloride ions that have been provided by the HCl in that solution. So I do also need to be able to show equations for this and probably name what's made. So I'm going to do the plus magnesium, which we did see was reacting, and yeah, it's not going very fast, but that's what I expected. There we go, we can actually see a difference in rate now, where the organic acid is going slower than the inorganic acid. Inorganic acid is this one here. Right, so for this one, we're going to go ethanoic acid plus magnesium goes to, because it is reacting, it's not an equilibrium, goes to, now, we know that acid plus metal gives hydrogen gas, so let's put that in there. And it's going to make magnesium ethanoate. So magnesium has a 2+ charge, but you'll notice that ethanoate is 1-. So I'm going to need 2 of those ethanoate ions. I've taken the negative charge off because this is now a salt. Okay. Now if I need 2 of those, I need 2 of those. My second one, so sorry, just to reiterate, this is called magnesium ethanoate. Right, And then my other reaction, which was hardly going at all, in fact, we're starting to get a few bubbles there, but it is going very slowly, was ethanoic acid plus sodium carbonate. Now, being a carbonate, I know that those bubbles are CO2. Because it's an acid plus a base, I know that there's water. And it's now going to make sodium ethanoate. Sodium's a 1+ ion, so I can just plug those two together like that. However, I notice that there's 2 sodiums in this equation, so I need 2 sodiums here, so that's 2 of that. Or if I need 2 ethanoate ions, I need 2 ethanoic acids. So the name of this is sodium ethanoate. So there we go, there's a wee overview of our carboxylic acids. You'll notice that they end in anoic acid. You'll notice that you have to remember to include the carbon with the functional group when counting the numbers of them. They are made by oxidizing a primary alcohol using a system called reflux, which increases our percentage yield. And we notice that they do have a pH below 7, but it's not as low as the same concentration of a strong acid.